Okay, this is Mr. G and inclined planes. That's a fancy word for a ramp. So yeah, it's a ramp. You take a board and you tilt it at some angle. All right, so here's the ground. All right, and I don't know what you put under here, some books or something, a piece of wood. Who knows? It's a ramp and it's inclined. And the incline is measured by this thing called an angle. And the angle is right here. And that angle is denoted by this Greek letter theta. And it's measured in degrees. So the angle might be theta equals 30 degrees, as an example. Just to refresh you on what degrees mean, let's see here. There's a thing called a protractor. Let me find one for you here real quick. Protractor. I think it's a protractor. Protractor. There we go. So here's a protractor. Take a picture of this guy. Well, you may have seen these before. I'm thinking in your math class. It's geometry, all right? So, protractor. Again, this is just a refresher on angles and what it means for something to be at an angle. So then, again, let's say that we have here's the ground, and there's a board here, and this guy actually starts the 0 point is right here, all right? And so we have this ramp, and it's angled up like this. And you'll see here, the angle is 30 degrees. So there's a ramp, and it's angled at 30 degrees. We could make another one a little bit steeper if you want to. There's a ramp, and this angle, theta, from here to here, it's 60 degrees. Okay, and then you keep angling it higher and higher and higher until you are at the, you're pointing straight up in the air. What the heck? Yeah, so this angle, theta, that's 90 degrees. So we will be dealing with ramps that are angled somewhere between 0 and 90 degrees. 90 is pretty darn steep, though. Now let me see if I can find the original thing I was writing about. Hang on. Here it is. Yep. Okay, so angles. Now we've got angles out of the way here. Here's a block sitting on this inclined plane. And we use a lot of blocks, right? So that block has a mass m. In this case, let's just say it's 1 kilogram. And this is taking place near the surface of the Earth. So there's a force called gravity. And there's the acceleration of gravity, little g. For our purposes, we're going to say little g is about 10 meters per second squared. So objects on inclined planes, besides gravity acting on them, there's also the inclined plane pushing it up that keeps it from falling. So we've got this whole thing with free body diagrams again, which are little arrows drawn on the object to show you what forces are acting on it. It's the usual forces, right? So in this case, a free body diagram we'll have a downward force, and that's equal to mg. We could even put a number on that if you wanted to right here, because the mass is 1 kilogram, and the value of little g is about 10 meters per second squared. And so that means that the weight of this guy, mg, well, 1 times 10 is 10. And you better know this by now. I'm serious. A kilogram times a meter per second squared is called a newton. So the weight of the block is, it's about 10 newtons. That hasn't changed any. What has changed is the normal force acting on the block. That normal force is the force that the inclined plane exerts on the block. It used to be that it was straight up in the air and it was equal to mg, but it's not now. That force is perpendicular to the incline, n, and it's no longer equal to the weight of the object, okay? So this is your basic free body diagram for the forces acting on this object. There's a normal force and there's the weight here. And the normal force is less than the weight of the object. So now what happens is, well, exactly what happens? Well, this thing, if there's no friction between the block and the incline, if it's slippery, it'll start to slide this way. And the force causing it to slide down the incline is gravity. But its acceleration is going to be less than 10 meters per second squared. So the inclined plane has the effect of diluting gravity. It makes the effective force of gravity weaker, right? So let's figure out exactly what is the acceleration of this thing going to be. How fast is this object accelerating? At what rate does its speed start to increase? Say every second it's sliding down the incline. So here's how to do this. And if you're still with me so far, that's great. You haven't fallen asleep yet. Because it's going to be on your next test, which is next week, maybe. All right, so here's the ground. Here's an inclined plane. And, let's just say theta's 30 degrees. I love 30 degrees. And here's your block. Sitting on here with a mass m. Guess what? It's 2 kilograms. What? That's crazy. 2 kilograms. And furthermore, there's no friction. So it's slippery. Like a road on ice, right? Or like it's a cart with wheels on it, so there's no friction. It's going to start to accelerate down the incline. And so the question is, how much is that acceleration going to be? So here's how we do this. First, step 1, free body diagram. In case you haven't familiar with that term, free body diagram. So the forces acting on this guy are its weight, mg, and there's the normal force, the force that the ramp exerts on this thing, which is perpendicular to the ramp. That means it's 90 degrees. And that force is denoted by N. And that's it. So then which of these forces causes it to accelerate? It's gravity. Gravity is the force causing it to accelerate down the incline. So then how do you deal with this? I'm going to tell you. Without going into a lot of geometric detail here, basically mg is resolved into two forces, two components that are perpendicular to each other. Part of gravity wants it to accelerate this way, and that component of gravity is equal to the actual weight, mg, times the sine of this angle. So it's mg sine theta. All right, and then there's another component of gravity that's acting perpendicular to the incline, and that force is opposite N. So it's this way. And that component of gravity is mg cosine theta. All right. So to do this problem, I know you guys are used to doing problems, some of you anyway, that draw free body diagrams, where we have an xy like this. For problems on inclined planes, our xy is drawn like this. So the axis is tilted for this problem. So now downward becomes the positive direction. So then I'm going to write Newton's second law, which you should know is net force is ma. So look at the picture here. What is the net force causing this to accelerate? It's not n. N is pointing perpendicular to the incline. It's accelerating this way. So there's only one force component pointing that way. And it's this guy right here. And that component is mg sine theta. So mg sine theta is ma. There's no friction. There's no opposing force. So this guy's not going to be like mg sine theta minus some other force. There is no other force, right? It's just gravity and the ramp acting upwards on it at an angle called the normal force. So now, math. Well, first of all, look at both sides of the equation. Here's an m and here's an m. So yeah, they cancel. So basically, the acceleration, we're already done. The acceleration of this object is equal to little g times sine of theta. Boom, you're done. But you do need to know, though, what is sine of 30 degrees? So for this, you could use your calculator. You could memorize it. All right. But since most of you aren't using calculators, and you might not be good at memorizing things here, you're going to be provided with a list of common sines and cosines and tangents of angles. So it turns out that sine 30 is equal to 0.5. And there are no dimensions here, no units, it's just 0.5. Right? So A is equal to, G is 10 meters per second squared, and sine of 30 is 0.5. So then 10 times 0.5 is 5. So this object has an acceleration of 5 meters per second squared. So its acceleration is half of what it would be if it were just falling straight down. And the shallower the angle is, the smaller its acceleration is going to be. And so then, yeah, you need to know how to do this particular problem. All right. So for now, let's just go ahead and pause that, and we'll do another video here in just a minute or so.